Hi everyone, we will continue exploring the topic scientific computing for chemists. In this session, we will learn a bit about optimization and root finding. This presentation is based largely on the information provided on the online book Scientific Computing for Chemists with Python by Charles J. Weiss. Optimization is the process of improving something to the point where no further enhancement is possible. In practice, this often means maximizing or minimizing a specific quantity. Whether consciously or not, we chemists frequently engage in optimization. For example, in tasks like molecular energy minimization, regression analysis, or the application of various machine learning algorithms. Optimization functions often aim to find the minimum of a given mathematical expression, commonly referred to as objective function or cost function. For instance, optimizing a molecular conformation involves minimizing its energy. In this context, the objective function is the one that computes the molecular energy based on a specific set of input parameters. The optimized module in the SciPy library offers a variety of tools for performing mathematical function optimization. The minimize function is versatile. It can handle both multivariate functions with multiple inputs and univariate function with a single input. In contrast, minimize underscore scalar is specifically designed for univariate objective function only, so function with a single input. Another set of powerful tools in optimized module are the root function and root underscore scalar functions. Much like minimize, the root function is capable of finding the root of both multivariate having multiple inputs and univariate having single input functions. On the other hand, root underscore scalar function is specifically designed to find the root of a univariate function having single input. These functions are essential when you are solving equations where the goal is to find the input values that make the function equals to 0. Let's explore the syntax of optimize.minimize function and optimize.minimize underscore scalar function. If we aim to minimize an objective function with a single independent variable and no known bounds, the optimize.minimize underscore scalar function is typically a good choice. As you can see in the arguments, we only have objective function. We don't have any other arguments. When minimizing an objective function with a single independent variable and known lower and upper bounds, we can modify optimize.minimize underscore scalar function by adding two arguments, bounds and method. Here, the bounds specify the starting and ending values of X domain to search, starting and ending values in the X domain to search. Setting method equals to bounded applied a constrained optimization approach, which means that the optimization is restricted to certain region, in this case the upper and lower bound of X domain. If we need to guide the search direction between 2 points, we can use the bracket equals to A and B argument with optimize.minimize underscore scalar function. The bracket equals to A comma B indicates that search will proceed from A to B with an expectation that f of B is going to be smaller than f of A. So in other words, it just shows you in which direction the optimization is going to take place. When minimizing objective function with an initial guess or starting point, we should use optimize.minimize function and provide the initial value. So this is initial guess, and we have objective function in the arguments. Now, let's walk through an example related to potential energy calculations. Shown here is the Lennard-Jones equation, which describes the potential energy as a function of distance r between two atoms. This equation serves as the objective function for our minimization problem. The potential energy function P_LJ is defined here. This customized objective function indicates that it takes a radius measured in angstroms as input and returns the potential energy in units of kilojoule per mole. Inside the user-defined function, epsilon and sigma are assigned values of 4.1 kilojoule per mole and 1.77 angstroms respectively. The function also incorporates the Lennard-Jones potential energy equation as shown here. Next, we will apply a type 1 optimization using the minimize_scalar function with the three arguments: the objective function, the bounds, and the methods. For bounds, we specify the lower and upper bounds of the X domain, and we select bounded to perform constraint optimization. We got this result after the optimization. We found the minimum when x equals to 1.986 and y equals to negative 4.09. Okay, now let's visually check if we have found the correct minimum value. First, we will create the x values for plotting using the arrange function ranging from 1.7 to 6 with an increment of 0.01. We will then feed these x values into our user-defined P_LJ function to calculate the corresponding potential energy values. In the first plot, we will display x values against their potential energy, PE, and label the curve as the energy function. Separately from the continuous curve, we will also plot a single point representing the minimum, since we know the x value of the minimum is stored in opt.x. Using the plot function, we will add this point with the argument opt.x, P_LJ opt.x. So having this x value, we can calculate the potential energy, and this is where we find the minimum. These are just x and y coordinates of the minima, and we will use the point and label minimum as a legend. Finally, we will label x and y axis and add a legend. The resulting plot will look like the one shown on the right. You can clearly see the potential energy well for the distance between the two xenon atoms, and the minimum is nicely highlighted with the point. Now let's run the code in the Visual Studio Code environment. First, we begin by importing the essential Python modules: NumPy, SciPy, Matplotlib.pyplot. Next, we define the potential energy function, PE underscore LJ. This is our custom objective function, which takes the radius measured in angstrom as an input and returns the potential energy in kilojoules per mole. Then we use the minimize scalar function from the scipy.optimize module to perform the minimization. This function takes three key arguments: our objective function, bounds, and the method. Finally, we create two plots. The first shows the potential energy as a function of radius. The second highlights the minimum point on this curve, plotting it at x equals up to dot x and y equals PE underscore LJ of opt dot x. Let's go ahead and run the code by clicking the play button. Once executed, the code will return optimization results, and we'll see the same plot that was shown earlier in the slide. There's a minimum point right here. Potential energy versus distance plot. Let's dive into another example, this time from quantum physics. Fortunately, in our previous session, we were introduced to SymPy for handling symbolic mathematical expressions. So these lines of code should feel quite familiar. First, we import the necessary modules: SymPy for symbolic expression, NumPy for array operation, matplotlib.pyplot for plotting, and sympy.physics.hydrogen for accessing built-in radial wave functions for hydrogen. Next, we define the symbol R. Remember, we discussed earlier that a symbol is different from a variable. We cannot directly assign a value to a symbol. Instead, we use subs function to substitute a value when needed. In this code, rather than manually writing out the full expression, we will bring in the built-in radial wave function using the R underscore NL function, and we will store it in a variable called psi underscore expression. The R underscore NL function, this is a built-in function for hydrogen, takes three main inputs: n, the principal quantum number, an integer that take values like 1, 2, 3, 4, and so on; L, the angular momentum quantum number, an integer that can range from 0 up to n-1; R, the radial coordinates. There is also another optional input Z, which indicates atomic number, 1 for hydrogen, but the default is 1 for hydrogen. In this case, we specified n equals 3 to select 3s radial function, L equals 0 for angular momentum quantum number, and the symbol R to represent the radial coordinates. After running these lines of code, we obtain the equation shown here. Next, we use the lambdify function to convert our symbolic SymPy expression into a regular Python function. In this case, we pass three arguments: R as the input variable, psi underscore expr as the equation, and NumPy as the module to handle array-based calculations. In this maximization example, our goal is to find the radius at which the probability of finding the electron is highest. The normalized probability is given by the expression psi square times r square, where r is the distance from the nucleus And we now plot this function psi squared times r squared over this radius r, ranging from 0 to 40 with an increment of 0.1. The resulting graph is shown on the right. Now that we have visualized the objective function psi squared times r squared, we can clearly see its shape. It has 3 peaks, 2 smaller ones and 1 dominant peak. Our goal is to find the maximum value, and to do that, we will use the minimize underscore scalar function. However, since minimize underscore scalar function is designed to find the minimum values, we will need to negate the objective function. So instead of maximizing psi squared times x squared, we minimize negative psi squares times x squares. This trick allows us to use a minimization function to locate the maximum point. You will also notice something else in here. Instead of defining a full user-defined function with def and return structure, we use a lambda function here. A lambda function is just a more compact way to define simple one-line functions when a full function definition isn't necessary. To define a function using a lambda expression, we start with the keyword lambda, followed by the independent variable, colon, and then function definition. The variable to the left of the colon represents the parameter that would typically go inside the parentheses of a standard function definition. Everything to the right of the colon is a user-defined function. Here, negative psi squared x squared. Upon execution, we receive a message indicating that optimization process has successfully terminated. This message includes the termination criteria along with the tolerance value. It also informs us that the minimum value was found at a specific y value and x value. Additionally, it provides the details about the number of iteration and evaluation performed. In this case, the minimum value was found at x equals 0.74 for the objective function. When we examine the plot, we can observe that this point corresponds to the smallest peak, which represents a local minimum rather than the global minimum. In this particular example, we know that the global maximum lies between 10 and 20 angstroms. To find it, we can use the type 1 optimization function, specifying lower and upper limits. Essentially, we are working with the same minimize function, minimize underscore scalar function, but with the 2 additional arguments, bounds and method. We set the bounds to 10, 20 and the method to be bounded for the constraint optimization. Upon execution, the solution is found at x equals to 13.074. Looking at the plot, we can confirm that this represents the global minimum for the objective function. In other words, it corresponds to the global maximum for the function. This example highlights how prior knowledge of the objective function allows us to define the bounds effectively, ultimately leading to the global maximum. Not all objective functions depend on a single independent variable. Some objective functions involve multiple independent variables. Let's explore a multiple minimization example. the tandem equilibrium reactions involving three different isomers. In this case, the isomer A, B, and C are in equilibrium with one another, with equilibrium constant K1 and K2. First, we assign the equilibrium values of 5 and 0.8 to K1 and K2 respectively. Next, we define an objective function obj underscore func, which takes an input guess. If we look at the line below, we can see that the variable guess is an array containing three input values. These represent the initial concentration of isomer A, B, and C in mole per liter. Based on these concentrations, the reaction quotients Q1 and Q2 are calculated within the function. The quality of the isomer mixture is then determined by how closely the reaction quotients match the equilibrium concentrations. In other words, the quality of the solution is sum of the squared differences between the reaction quotients and the equilibrium values. In summary, the user-defined function obj underscore func takes multi-variable input, guess, and returns the quality value as an output. At this point, the function has been defined, but we haven't used it yet. To do so, we first need to assign three values to guess variable. Then we optimize the function by applying the minimize function. As we discussed in the previous slide, this function takes the objective function obj underscore func and the initial values as inputs. After executing the code, we obtain the result shown below. The message optimization terminated successfully indicates that the optimization ended normally. The algorithm found the solution without errors or exceeding limits. Success equals to true, confirms the optimization successfully converged, meaning that it has reached the minimum satisfying the tolerance settings for the optimization. Status code 0 typically means OK or successful convergence. Fun equals to 9.4297 to the exponent of negative 14. This is the value of the objective function at the solution, which is very close to 0, a strong indicator of a good result. And then the optimized variable values, the value of your input parameter, A, B, and C concentrations. Nit equals to 8. The number of iterations the algorithm performed is 8. Number of evaluation was 60, and NJEV indicates the number of Jacobian evaluations. Evaluation of the gradient, first derivative of the objective function. And it shows us the Jacobian matrix, Jacobian solution, which is the gradient, first derivative gradient at the solution. These small values suggest the function is nearly flat, a good indicator of a local minimum. And then we have inverse of Hessian matrix, which is the second derivative. This matrix is used in quasi-Newton methods to estimate curvature near the solution, which affects step size and direction during optimization. This will be out of the scope. In summary, it shows the minimum y value, which is the best quality value, and the corresponding x values, A, B, and C concentration. Okay, let's run the code in the Visual Studio Code Editor. As always, we start by importing the necessary modules, NumPy, SciPy, and matplotlib.pyplot. Next, we assign values to the constant k1 and k2. We then define a user-defined function, obj_func. This function takes an input array named guess, which contains the concentration of A, B, and C. It returns a value that reflects the quality of the mixture. The quality is how closely the gas concentration matches the equilibrium conditions. To optimize obj_func function, which is our objective function, we use the minimize function. It takes two arguments, the objective function itself and the guess variable, which contains the concentration of A, B, and C. Let's run the code by clicking the play button. Here we obtain the optimization results, which contains X values and Y values. X values are the concentration of A, B, and C, and Y value is the minimum values. Root finding is the process of determining where a function equals 0. We have encountered root finding in mathematics courses over the years. For a univariate problem, this can be straightforward, but for multivariate problem, optimization algorithms can be very helpful. Just like the minimization function, there are two versions of root finding functions: optimize.root_scalar function, optimize.root function. The root function can handle both univariate and multivariate problems, while root_scalar function is limited to univariate functions. Both functions require the target function for root finding, which is similar to objective function. Additionally, the root function also needs initial values, while root_scalar can take an optional range where the function changes sign at the two endpoints. The sign changes between these 2 points. The coding process is quite similar to the minimization optimization. First, we define a user-defined function. In this case, it is a radial wave function for the hydrogen 3s orbitals. Unlike the previous example, we won't be using the SymPy physics.hydrogen module. Instead, we will manually define the wave function, which we will call orbiter_3s. The input is r, radius, and the output is the value of the wave function. Although the plotting part of the code isn't shown here, we created a range of x values and the corresponding y values, psi_3s. To find the roots, we use the root_scalar function with the two different brackets between 0 and 3 and between 5 and 10. When printing the node 1, we obtain the following results. Converged true, the algorithm successfully found the root 0 of the function within the specified tolerance. Flag equals to converged confirms the method stopped because it is converged, not due to an error or exceeding iteration limit. The function was evaluated 11 times during the root finding process. The algorithm completed 10 iterations before converging. The value of the root is 1.9019, and this is the root found, the value of x such that fx equals to 0. Method equals to Brent Q indicates Brent's method was used which is a combination of bisection, secant, and inverse quadratic interpolation. The two values that we found as a root is 1.9019 and 7.0980. Okay, let's run the code in the Visual Studio Code Editor. As usual, we begin by importing the required module: numpy, pandas, scipy, matplotlib.pyplot. Next, we define the wave function orbital underscore 3s. This function takes the radius as input and returns the corresponding wave function values. To prepare for the plotting, we generate xgrid and compute the corresponding y values, psi underscore 3s. Now we use root underscore scalar to find the roots of the wave functions. Specifically, we search for roots in the interval between 0 and 3 and 5 and 10. The function takes two arguments, the objective function and the specified bounds. After that, we generate the plot as shown on the presentation slide. Okay, let's run the code by clicking the play button. As anticipated, the code returned the optimized results and it displayed the plot potential well indicate those two location of the roots. In this session, we explored two different optimization problems: minimization and root finding. We demonstrated examples of both. Minimization was achieved using the minimize underscore scalar function or minimize function, while the root finding problem was solved with root underscore scalar function or root function. The key similarity between these two functions is that both require a function to optimize. Additionally, both may require boundaries for the optimization process. The results represent here focus on univariate optimizations, but similar functions such as minimize or root are particularly valuable for multivariate optimization problems. Multivariate optimizations can be significantly more challenging to perform manually, making these functions essential for tackling such problems efficiently.